Alright, thanks for watching, and today I want to show you a very neat product rule but for Limsups. And by the way, for this video you don't need to know what a Limsup is, just think of it as the biggest possible limit of a sequence. Now, in general, it is not true that the Limsup of Sn times Tn is equal to the Limsup of Sn times the Limsup of Tn. And in fact, let me give you a very nice counterexample. So consider the following sequence. So Sn, it alternates between 1 and 0. So 1, 0, 1, 0, 1, 0, 1, 0. So this is Sn. Again, it goes between 1 and 0. And in particular, the Limsup of Sn, so the biggest possible limit of Sn is just 1. On the other hand, consider the following sequence, Tn, which alternates between 0 and 1. So it's 0, 1, 0, 1, etc., etc. Well, in this case, the Limsup of Tn is also 1. So the biggest possible limit of Tn is also 1. But then, what is Sn times Tn? Well, notice, for every n, at least one of them is 0. Therefore, the product of the two is also 0. And in particular, Sn times Tn is 0, and the Limsup of that is also 0. So therefore, the Limsup of Sn times Tn is the Limsup of the 0 sequence, which is 0, and that's different from 1 times 1, which is the Limsup of Sn times the Limsup of Tn. So in general, the product of Limsups is not the Limsup of the product, but I want to show you that under a very mild assumption, this is actually true. So fact, namely, if one of them converges, then it turns out this is true. So fact, if, let's say, Sn converges to S, where S is positive, let's say, then the Limsup as n goes to infinity of Sn times Tn becomes S times the Limsup of Tn. And remember, if a sequence converges to S, then the Limsup equals to the limit. So in fact, in this case, the Limsup product rule is true. So it's the Limsup of Sn times the Limsup of Tn. Okay, and let's see how we can show this. So first of all, let's give Limsup of Tn a name, so proof. First of all, let T be the Limsup as n goes to infinity of Tn. Okay. Here's how our proof is gonna work. We will show that this is less or equal to that, and then this is less or equal to that. So a very typical analysis way of doing this. So step 1, let's show one inequality. And here's the only issue. Well, T, it could be finite or it could be infinite. So let's do it by cases. So case 1, T is finite. Then, or if T is a real number. Now here's the thing. Again, you do not need to know anything about Limsups. Because, remember, there's this beautiful fact that even though Limsup is an abstract concept, we can always attain it with a subsequence. So by this very complicated proof I've done a couple of videos ago, we know there is a subsequence T and K with T and K converging to the Limsup. So I can just draw a picture. So this is, if you want, the sequence Tn. And suppose this is the Limsup T, then we know there is a subsequence, in fact a monotone one, that converges to T. But then the nice thing is, the proof isn't too bad then, because consider now the subsequence Tnk times Snk. So you take Sn, but with the same values of Nk. So now consider Snk times Tnk. Well, you see Sn converges to S, so the subsequence converges to S, and Tnk converges to T, so therefore the product Snk times Tnk converges to St. So what have we found? We found a subsequence of Sn times Tn, kind of like that. So if you want, this is Sn times Tn. We found a subsequence that converges to St. Like this. However, remember what the Limsup of Sn times Tn is. It's the biggest possible limit. It's the supremum of all the limit points. So in fact, the Limsup of Sn times Tn must be bigger than that. So if you want, since if on the Limsup Sn times Tn is the largest possible limit, of the sequence Sn_Tn, and St is one possible limit of the sequence Sn_Tn. Again, here's the subsequence. We actually must have that the Limsup is bigger than St. So, Limsup of Sn_Tn must be greater or equal to St, which I would like to remind you is the Limsup of S times the Limsup of T. So in that case, we're done, where we assume that T is finite. But then, if T is infinite, the case is even easier. So case 2. Suppose T is infinity. Well, if a sequence, if the Limsup is infinity, what this means is that, well, there must be at least one subsequence that goes to infinity. So there is a subsequence of Tn, called, let's say, Tnk, with Tnk goes to infinity. Okay. Tn, take care of yourself. Okay. But then, what do we know? You see, Snk times Tnk. Well, this goes to S, and this goes to infinity, and since S was positive, this whole thing must go to infinity. So again, infinity is one possible limit of S and Tn, so therefore the Limsup is even bigger. So again, by before, the Limsup of Sn times Tn, that then becomes greater or equal to the limit as k goes to infinity of Snk times Tnk, and that's infinity, which is, if you want, the limit, the Limsup of Sn times the Limsup of Tn. Because the Limsup of Sn is just S, the Limsup of Tn is infinity. Lastly, in the case t equals minus infinity, this is even easier because we just want to prove an inequality here. Because look, what this is saying is that is Limsup of Sn times Tn, is that greater or equal to the Limsup of Sn times the Limsup of Tn? The question, but you see, Limsup of Sn is S, Limsup of Tn is minus infinity. So the question is this number always greater or equal to minus infinity? And yes, it is. Any number, even plus or minus infinity, is greater or equal to minus infinity. All right, and so in this case, at least for this case, we are done. So we have shown that Limsup of Sn times Tn, it's greater or equal to the Limsup of Sn times the Limsup of Tn. And now we want to show the opposite inequality, but this is actually quite fun. We'll do a proof by laziness, which means we'll just adapt step 1. So first of all, remember Sn, it converges to a positive number S. So in particular, eventually, we may assume that Sn, all the values of Sn are positive. You can formalize this if you want. And so without loss of generality, since we're assuming that n is very large anyway, let's assume that all the values of Sn is positive. So without loss of generality, since, again, Sn converges to S positive, let's assume Sn is positive for all n. It's going to happen eventually anyway, so let's just assume it's true from the beginning. But now, let's consider the Limsup of Tn. Well, this is the same thing as the Limsup of, and again, you'll see why I do this in a second, 1 over Sn times Sn times Tn. Why did we do this? Because we want to make Sn times Tn appear. But here's the thing, by what we've shown, what do we know? We know that 1 over Sn, well, it converges to 1 over S, because Sn converges to S. So, by step 1, we actually get that it's greater or equal to the product of the Limsups. 1 over Sn times the Limsup, no, this is greater or equal to 1 over S times the Limsup of Sn times Tn. But then you can just solve for this and you ultimately get that the Limsup of Sn times Tn is less than that. And so what we know is the Limsup of Sn times Tn becomes less than or equal to S times the Limsup of Tn, but that's just the Limsup of Sn times the Limsup of Tn. And then we're done. And we can stay home happy. All right, thank you very much.